Hello everyone, and today we are going to do the tutorial 2 of Introduction to Robotics. And as a first step, I am going to do a brief recap of what you have seen with Professor Zhao during the lectures. So we are going to talk about transition metrics, frame assignment, the Jacobian, and a little bit about kinetic and potential energy. And so we're going to see all of this during the second and the third tutorials. The introduction of today will be a little bit first of transition, then the frame assignment, and then the Jacobian. So let's start first with a definition of the transition matrix that should be quite clear for you. We have that the transition matrix from frame I to frame J is basically this block matrix in which there is the rotational part from block I to block J, the vector, so the position of the origin of frame I to the origin of frame J, and then a 1 over here. So the dimension, so basically the indexes, I is the final frame in which you will end up when you apply this transformation matrix, and J is the actual frame in which you are currently working on. Therefore, if you have, for example, let's say, a vector that is expressed in frame 4, and you apply the rotational matrix, okay, 0, 4, you will end up with a vector that is expressed in the 0 frame, okay? So this is what means final frame and actual frame, that the final vector in this case in which you will, the final frame in which you end up is the one that is on the upper part, in the upper appendix, and the actual frame, the current one, is the one that is in the bottom appendix. Then the dimension of a transformation matrix is 4 by 4, and obviously we have the rotational matrix that is a 3 by 3 matrix, and the vector of position that is a 3 by 1 matrix in which there is x, y, and z. Okay? Now, there are 3 basic rotational metrics, and they are around the 3 axes, x, y, and z. You should be quite familiar with this. You have seen it also during the first tutorial. And the first one is the rotation around x of alpha degree. So you have a 1 in position 1, 1, and then you have a block of a 2 by 2 matrix that is cosine minus sine of alpha, and cosine of alpha. And then there are the others that are just basically a shift into this structure. But as you can see, the elements are always the same. So these are the basic rotation metrics. And now let's go through a little bit how to assign the frames, okay, to a robotic arm. I've introduced, I think that the other teaching assistant introduced already to you this flow chart that I created in order to make it easier for you to assign the frames. And it works basically like this. You start with the frame, basically frame 1. You draw the I and the I plus 1 axis. So given 2 joint, you are going to draw the axis that go through the revolute or prismatic joint. Then you identify the common perpendicular between these 2 axes. And in this case, there can be 3 cases. Is there an intersection or not, or they coincide? So if there is no intersection, then you end up in this red case. you have to place the frame I at the origin when the intersection touches the ith axis, okay? If instead there is an intersection between the two axes, you have to place the frame I origin in the intersection point, and if they coincide, you have some freedom on where to place the frame I. So in practice, you can have these three cases. Let's say that this one is one joint, this one is the other joint, this one is one axis, this one is the other axis. In this case, there is no intersection between the two axes. So this one is axis I, and this one is I plus 1. There is no intersection between the two, okay? This one is the perpendicular, and therefore I have to place I over here, okay? What happens if instead there is an intersection? Well, in this case, join 1 can be something like this, and join 2 can be something, let's say, like this. I draw axis 1, I draw axis I plus 1. Well, in this case, the intersection line between the two is just this point, right? Because there is indeed the intersection, so this one is the perpendicular between the two. And therefore, I have to place the origin of frame I here, as you can see. So we are in this green case over here, okay? Now, finally, you have maybe, let's say, two joints that are done like this, okay? You have one joint here, and another one like this. Over here, maybe they are connected in this form. In this case, you have that the two axes coincide. The axis of I and I plus 1. And in this case, you can place the origin of the frame I wherever you want along this line. Okay, this is what these first three cases mean. Then you have to assign Zi pointing along the ith axis. And in this case, for example, let's say that, let's take the simple case over here. In this case, you have that, imagine that this joint works revolute in this form. Therefore, you have to point the z-axis using the right-hand rule, in which you basically have to, let's say, grab this axis and point your fingertips in the same direction of the rotation, so in this form, and then you have your thumb that tells you where the z-axis is. So in this case, it will be up. So you place Zi like this. In this second case, let's say that we have the same kind of rotation. It works in the same way. Therefore, we have to place Zi here, okay? Because we have to place it still along the axis of joint I, okay? And in this case, once again, we have, let's say, the rotation in this direction, and therefore, let's say that we decided that the origin of frame I is over here because it's more convenient for us for whatever reason, and then you have that Zi works like this. It's over there. Okay? So now, yes, so to place the x-axis, we have once again a choice based on the fact that there is or there is not an intersection between the axes. If there is no intersection, you just place x along the perpendicular between the two axes. So in this case, x will be along here, xi, easy. If instead there is an intersection, you place xi Here we are in the green part, normal to the plane where the height and the height plus 1 axis lay. What does it mean? It means that basically this axis here and this axis here create a plane. What does it mean? That there is all this part here, okay, that is the plane described by these two axes. In this case, you have to take something that is perpendicular to this plane. So x will point outward, something like this. Okay? And finally, if there is a coincidence between the axes, you can just point xi freely. Okay? Finally, you have the last step that is trivial because you just have to complete in order to have a right-handed frame, and you can use the right-hand rule. So x, y, z, and you go on like this. And then you go on, and you go on for the height plus 1 frame, and so on and so forth, until you arrive to the end of the whole kinematic chain. So basically, you start from the frame 1, you go to 2, 3, 4, 5, 6, 7, whatever it is. And then, at the end of all this process, you place frame 0 and frame n. So to assign frame 0, either you place it to match frame 1, or unless it is said otherwise, because sometimes you have a manipulator in which it is more useful for whatever reason to place frame 0, let's say, I don't know, somewhere else because it is easier for the calculation, or because the exercise tells you so. So if frame 0 or frame n are placed in a certain way in an exercise, you have to keep it that way. Okay? Good. And this concludes a little bit our excursus on the frame assignment. I hope this refreshment of the discussion made it more easier for you. Now, let's go on with the Jacobian. Well, the Jacobian basically is what tells you the relation between the linear velocity and the derivative of the joint velocity. That is this q over here, okay? Therefore, it describes basically how the robotic arm is moving, okay? And what is it's the velocity of the end effector given the velocity of each one of the joint. Why it is very useful? Because a lot of times you don't want the end effector to be to move too fast or too slow, or you want it to have a certain behavior or to follow a certain trajectory. But at the end of the day, what you can control are the joints. So usually you can impose some velocity over the joint, and you want to understand how this velocity translates into a velocity of the end effector. So to understand this relation, that is very important, as I told you, there is this concept of Jacobian. The Jacobian is split in two parts. There is the Jacobian associated to the linear velocity and the Jacobian associated to the angular velocity. And they are basically stuck one on top of the other. Obviously, the linear and angular velocity are the one associated to the end effector in this case. Okay? And one way to compute the Jacobian is the velocity propagation method. Basically, you have to propagate the velocity from frame 0 to the end effector, okay, by using these formulas over here. The first one are for the revolute joint, the other one are for the prismatic joint. As you can see, In the prismatic joint, there is not the derivative of theta because the variable that is the variable of the joint is d. So the main difference between the two, as you can see, is the joint variable that in the Revolut case is theta, and you have a theta dot over here. And in the second one, it is d, so d contribute to the linear velocity. Okay? So Revolut, you have the derivative of theta, and prismatic, you have the derivative of the displacement. Okay? Now, another possibility on how to, let me go back one slide. So basically, why does this method gives you the Jacobian? Well, let me erase. Basically, it works like this. When you have the velocity, okay, associated from a frame, let's say 4 to 0, okay, it will be a function, okay, of the, it will be, you can rewrite it as a big matrix, okay, times all the joints variable. So the joint variable, let's say that we have, since we are in frame 4, we have an R, P, R, arm, something like this. You have theta 1, D2, theta 3, theta 4, okay, dot, 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 dot. And this part over here is the component associated to the linear Jacobian in this case, okay? So this is why it is used. Then another possibility that is probably the easier one is to compute it directly from the vector that connects the origin of the zero frame to the end effector. So as you can see here in this relation, you have just to take the partial derivative of this vector with respect to the joint variable to compute the Jacobian associated to the linear velocity. To compute, on the other hand, the Jacobian associated to the angular velocity, the only thing that you need is the are the axes. So when you have all the axes around which the joint are revolving or moving around, okay, you just have to multiply it by 1 if it is a revolute, so you will actually put the vector describing the axis, or you will put a 0, okay, if it is a prismatic, so there will be nothing over there, okay? Now, how to compute the singularities associated to a robotic arm? Well, the singularities are basically when a certain configuration of the joint, so a certain position, so a certain Q, makes the Jacobian, the determinant of the Jacobian equal to 0, okay? So if you take the determinant of the Jacobian, you put it equal to 0, the value of the Q's such that that determinant is equal to 0 are the singularities of the arm. Okay? And this basically concludes all our main recap of the transition matrix, Jacobian, and a little bit also on the frame assignment. Okay? And now we can go on with the actual exercises. So the first exercise, consider this arm over here as a I already gave you the exercises, so you can also follow on the PDF that I uploaded on Nestor. And it asks to draw a schematic of this manipulator with the axis of frame 0 through frame 3 labeled. Note that frame 3 has been done for you, and your solution should be consistent with the given frame 3. Also include the parameters D1, A1, theta 2, and so on. So, let me erase all this stuff. Okay. Now, this particular arm has the base frame. We have a base over here. Then we have a prismatic joint over here that we put this symbol for the prismatic joint. Okay, and he can move in this direction. Okay, and this distance over here is D1. Then you have a revolute joint. Over here. And then you have another revolute joint. And then finally the end-effector. Okay? Now you have that this one is A1 and this one is A2. Okay? And that's basically it. So at this point we can place, we have to follow all the scheme. So the axis of the first joint is this one, right? Because it is a prismatic one. The axis of the second is this. The axis of the third is this one. Now we have to draw the perpendicular between axis 1 and axis 2. The perpendicular is just along this line, so we can put it along this link between the two. And we place Z along here because it's the direction of motion. Okay. This one here is Z1. And since there is no intersection, you end up having X1 over here. Okay? Then we go to the second frame. And for the second frame, we have to look at the third axis. Also in this case, there is no intersection. So also in this case, the origin is placed here. And since it tells you that the rotation is counterclockwise, the z-axis is up. So this one is Z2. And then you place X2 along the perpendicular. Okay? Finally, we have the third one. The third one, it tells us the text of the exercise that it has to align with the third frame. So the third frame is placed, the third frame is placed like this. So it's already given for us, X3. Okay? Now I will just give you basically the, now we have to describe the DH parameters, as you can see in the slide. So the DH parameters, we can do the usual table. 1, 2, 3, and 4. Okay, now here you have A of I minus 1. Then you have alpha of I minus 1. Then you have D1 and theta I. Sorry, the I here. Now you have frame 1, 2, and 3. Okay, and another thing in this case the frame 0 is placed over here because it is placed congruent to frame 1, but with the joint variable placed to 0. So over here. If d1 is equal to 0, then the frame would be here. So here is s0, and here is x0. So the question to complete this table are basically the following. Is there any rotation around the x-axis to go from frame 0 to frame 1? No. Is there any displacement along the x-axis to go from frame 0 to frame 1? No. Therefore, here there is a 0, and here there is a 0. Then, is there any displacement along the z-axis to pass from frame 0 to frame 1? Yes. And it is exactly of d1. And is there any rotation? No. So there is a 0. Now, how do we pass from frame 1 to frame 2? Well, is there any displacement along the x-axis? Yes, there is. And it is exactly of a1, right? And is there any rotation around the x-axis? No. Is there any displacement along the z-axis? No. Is there any rotation along the z-axis? Yes. And it is of theta 1. Same thing for joint 3, that it is exactly a2, 0, 0, theta 2. And this concludes the second part of the exercise. Okay, so point B. And yes, so, okay, here you can see the schematic that I just described over here. And now, okay. Now we have point C and point D that are basically derive the forward kinematics for the manipulator. That is, find the matrix 0 to 3. Okay. How do you do that? Well, this comes directly from this table over here. So when you have this table, then you are basically done. Why? Well, because the transformation matrix basically works like this. Transformation matrix from 0 to 1 is equal to basically a transformation that is R displacement here. Well, let me write it as a P because it's better. From 0 to 1, and here from 0 to 1. Okay? So, if you look at here, there is no rotation neither along the x-axis, neither along the z-axis. Therefore, this R01 is just equal to the identity. Okay, here we have a 1, here there is 0, 0, 0. Therefore, we have identity here. Well, okay. Let me just 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay, here we have the usual free 0. Here we have a 1. And now the question is, what is this vector? What is the vector that connects the origin of frame 0 to the origin of frame 1? Well, it is just a vector of 0, 0, d1, right? Because there is just a translation of d1 along the z-axis, as it is written over here, right? So this is the transition matrix from frame 0 to frame 1, okay? Now, we just have to compute the transition from frame 1 to frame 2, okay? And how do we do that? Well, it's basically the same structure, just that it is from 1 to 2 and from 1 to 2. And in this case, we have that, is there any type of rotation from frame 1 and frame 2? Yes, there is. And there is actually just a rotation of theta I along the z-axis. Therefore, here we have one of the basic rotational metrics, the one that I showed you before over here. Here, the upper one, okay, the bottom one, okay, just with theta 1 instead of the alpha. And that is what you have to place in the upper left block of the transformation matrix. Okay, so let me go back. Okay, therefore we have seen that it has to be a rotational matrix along the z-axis of theta I, and therefore it is something like, here it was theta 2, and here it was theta 3. So it is something like this: cosine of theta 2, minus sine of theta 2, and then you have sine of theta 2, cosine of theta 2, then you have 0, 0, 1, 0, 0. Here we put the usual 0, 0, 0, 0. And now the question is there any displacement between, is there any displacement between frame 1 and frame 2? Yes, there is, but it's not in this case along the Z frame, but it is actually along the X frame, as our nice table tells us. Therefore, the vector here would be A1, 0, and 0. Okay? Now we can do the same thing for the third join, and I think it won't be a surprise that it looks quite similar, because also in this case we just have a rotation along the z-axis of theta 3 and a displacement, so a translation of A2 along the x-axis. Therefore, we have something like this: cosine of theta 3 minus sine of theta 3, sine of theta 3, cosine of theta 3, 0, 0, 1, 0, 0. Okay? And we end up here with just the vector of that translate the origin of A2 along the x-axis. So, because this one is the x component, this one is obviously the y component, and this one is the z component. Okay? Good. Now, it asks us to compute the matrix from 0 to 3, and from 0 to 3, the matrix is obtained just composing these three matrices. How do we do that? Well, the transformation matrix, the transition matrix from 0 to 3 is just the one from 0 to 1 multiplied by the one from 1 to 2 and multiply once again by the one from 2 to 3. Therefore, the multiplication of these two gives you something like this: 0, 1, that multiplies the transition matrix from 1 to 3, and then you obtain the solution. You can also think of as an heuristic to understand how to do this sort of multiplication with the indexes, that this one arrays with this one arrays with this, so you just end up with 0 and 3, so you obtain the transition matrix from 0 to 3. Okay, this one is a little mnemonic rule to remember this kind of multiplication. Okay, so let me erase this stuff. 1 second. Now the last question of our exercise asks us to compute the inverse kinematic. To compute the inverse kinematic, the only thing that we need is the last column of the transition matrix from 0 to 3. Why? Because the last column is exactly the vector that connected the 0 frame to the end-effector. Fine? So I will just put here the, so you could do that multiplication by yourself using those three matrices. Just believe me that the transition matrix 0, 3, okay, is something over here, then it has the free 0, then a 1 here, and as a last column, you have A1 plus A2 cosine 2, and then you have A2 sine of theta 2, and then you have D1. Okay, this one is the last vector. Okay, is the vector from frame 0 to the end effector, and therefore the direct kinematic is something like this: x, y, z is equal to this vector, right, over here. So it is the relation, the forward kinematics. So forward kinematics is the relation between theta 1, theta 2, theta 3, and d1 to xyz. Therefore, xyz is equal to this relation over here, a1 plus a2 c2, a2 sin 2, d1. Okay? Now to find the inverse kinematic, we just have to inverse this relation. So find the inverse of this relationship. And how do we do that? Well, we have somehow to notice a couple of things. First of all, we already have a relation, because the inverse kinematic, basically, we want something like this. We want that given as output, basically, of the relation d1, theta 2, and theta 3. Okay? And as input, something that depends on x, y, and z. So, as you can see, there is no dependency on theta 3. So, theta 3 does not appear over here, because here we were just considering the origin of the frame 3. So we are considering the forward kinematics from frame 0 to frame 3. Sorry, not to the end effector. And that's why there is this relation, and this relation is independent to theta 3. So theta 3 doesn't matter. And now we have that d1 is simply equal to z. So here we can just put z. And now we have to find some relation that connects x and y with theta 2. How do we do that? Well, we can also rewrite the first equality as follows. So x minus a1 is equal to a2 cosine of theta 2. Okay, and then we have the other one, that is y is equal to a2 sine of theta 2. Okay, so how do you do this? Well, you just divide one by the other, okay, and you can see that you obtain the tangent, okay, and therefore the relation that you obtain is just that y over x minus a1 is equal to the tangent of theta 2. Therefore, theta 2 is equal to the arctangent of y over x minus a1. Okay? And is exactly what you have to put here. Okay, and this concludes the second exercise. Sorry, the last point of the first exercise. Now, in the meantime that I erase This is the second exercise. Okay. So, as second exercise, we have these three matrices, and it's asked to us to derive the basic Jacobian relating joint velocity to the end-effector, linear, and angular velocity. Now, as I said before, the Jacobian can be computed in two ways. One way is the velocity propagation. The other way is the derivative of the vector that connects the zero frame to the end-effector, if you want the Jacobian from the zero frame to the end-effector. So, how do we do it in this case? Well, we don't have the possibility to compute the velocity propagation, but we have the vector that connects the zero frame to the end-effector. Why? Because we can just look at this last column of the transition matrix from 0 to the end-effector. Therefore, this one, so the vector P from the origin of the zero frame to the end-effector is equal to just the last column, so L1, C1, plus L2, sorry, yes, C1, C3, minus S1, D2, and then you have L1, S1, plus L2, S1, C3, plus C1, D2, okay? And then you have minus L2, S3. Now, since we have the vector, the only thing that we have to do to compute the Jacobian associated to the linear velocity, so JV, basic Jacobian, is to compute the partial derivative of P0e with respect to the first variable, that is theta 1. Okay. Then you have theta 1. Then you put, and this one will be a 3×1 vector because you have 3 elements. So you derive the first one, the second, the third obviously is 0 because there is no theta 1. Then you have the second variable that is d2. So you have to take, once again, p from 0 to e, and the derivative with the partial derivative with respect to d2. And also in this case, this will be a vector of 3×1. And then you do the partial derivative down like this with respect to theta 3. Therefore, this one is a matrix of 3×3. Okay? And it is the Jacobian associated to the linear velocity. I will not do the computation because they are just partial derivative. I think both of you can do some partial derivative of the sine and of the cosine. So they are fairly easy, and you can also find the calculation in the solution. Now, the question is about the angular, the Jacobian associated to the angular velocity. So 0 omega. How do we compute this? Well, it was written something like this. This epsilon 1 times Z1, epsilon 2 times Z2, epsilon 3 times Z free, right? And now the only thing that we have to be careful is to extract correctly these three vectors that are the axes around which the whole the joints revolute or move around. Okay. How do we extract this? Well, the only thing that we have are these matrices, and luckily for us, this is all we need, because it turns out that they are all expressed with respect to the zero frame. So this one is Z1 expressed in the zero frame, Z2 expressed in the zero frame, Z3 expressed in the zero frame, and therefore the first one, well, this epsilon here, it was 1 if it was a revolute joint, and 0 if it was a prismatic joint. So in this case, we have as a first joint a revolute joint, okay, because it's an RPR manipulator, and as a second joint a prismatic, and a third a revolute again. Therefore, this one is a 1 times Z, the axis. The axis, I will obtain it as the third column of the rotational matrix in the transition matrix T from 0 to 1. Therefore, it is exactly this column that is 0, 0, 1. Okay? I will tell you once again, the axis around which joint 1 rotate is the vector, it is at the end, so the third vector of the rotational matrix from 0 to 1. How to obtain the rotational matrix from 0 to 1? It is just the up left block of the transition matrix T from 0 to 1. Therefore, I look at the text of the exercise, and I can immediately see that it is 0, 0, 1. Okay? The second one, well, I'm unlucky. It's unlucky that I don't have the transition matrix from 0 to 2. But if I look a little bit better, I'm lucky that this one is a prismatic joint. Therefore, that epsilon is equal to 0. And for this reason, I don't need to know this Z, because this is just 0, 0, 0. Finally, I will do the same trick with the third joint. Therefore, I take a look at the transition matrix from frame 0 to frame 3. I extract the rotational matrix, that is the upper left block, and I take the third column. So minus sine 1, cosine 1, 0. Okay, and this one is the Jacobian associated to the angular velocity. Therefore, to recap how to compute the Jacobian, if you have this vector, the only thing that you have to do is to derive with respect to the joint variable, okay? So the first column of the Jacobian will be the derivative with respect to the joint variable of frame 1, of joint 1. The second column of the Jacobian will be the partial derivative with respect to the joint variable of joint 2. And the third column will be the partial derivative with respect to the joint variable of joint 3. To compute, on the other hand, the Jacobian associated to the angular velocity, what you do is put as first column the axis with respect to the axis of the first joint, multiplied by 1 if it is a revolute joint, and 0 if it is a prismatic joint. So in the second case, these are all zeros, because indeed it is a prismatic joint. And in the third case, I just extracted from the transition matrix the actual axis Z3. Okay? I hope this is clear, and this concludes also the second exercise. Let me have a sip of water. Okay. Now we go to the third and last exercise for this tutorial. Okay, so in this case, we have another free joint manipulator in which there is this form here. So we have the first joint like this, the second joint like this, the third one is facing us once again, and then there is the end-effector. The exercise already gives us the x1 that coincide with x0, and then we also have z1 that coincide with the z0, and it is pointing outside of the blackboard. Okay, so it is something like this. Okay. In this direction, let me do like this just to clarify a little bit better, but it is actually pointing toward us, okay? And also it gives us the end-effector. X4, and this one is Z4. Okay, let me see if you can see. Yeah, okay, perfect. Okay, now the first question is to define the DH parameters. And how to do that? Well, we have to do the same thing as usual. So let me draw all the columns. So A, I minus 1. Then you have alpha, I minus 1. You have D1, Di, then theta I. And then you have joint 1, 2, 3, and 4. Okay? So in this case, there is 3 joints, but we also want the fourth frame. So the relation also with the fourth frame. Now, what is the relation between the 0 frame and the 1 frame? How we pass from the 0 frame to the frame number 1? Well, the only difference that there is between the two, well, let's start like this. Is there any difference along the x-axis? No, right? There is no difference because there is no rotation along the x-axis, because it would mean that the 2z wouldn't be one above the other, right, if there is any difference. And there is no translation, so there is no rotation and no translation. Therefore, the alpha I minus 1 and A of I minus 1 are both equal to 0. Okay, this is 0 and this is 0. Now, is there any translation along the z-axis between the two frames? No, because they are placed in the same point. So also this one is a 0. And now the question is there any rotation along the z-axis? Well, yes, because this one is a revolute joint. I can actually rotate of theta 1. In this case, they are in the same position just because theta 1 is equal to 0 in this particular configuration in which the arm is placed. But in general, this one is theta 1. Okay? Now, how do we place the second frame? What we have to do is to draw the axis. Okay, so one axis is, well, okay. One axis is coming outside of the blackboard. The other axis instead is along here. What is the perpendicular between these axes? Well, the only perpendicular that there is the line along the link between the two joints. And why is that so? Because if one line is like this and the other one line is like this, okay, there is only one line that connects them. And yeah, sorry. Yeah, I'm sorry. To place frame 2, we have to look at joint number 3, not joint number 1. I was placing again joint number 1, but we already have it because it's already given. So we have to place joint number 2, but it doesn't change much because also in this case we have that the axis of the joint 3 is coming outside of the blackboard. Therefore, the only perpendicular between the two axes is the line along along the link, okay? And therefore, I have to place the origin of the second frame in the intersection between the perpendicular and the axis, so exactly here. Now I have to place the Z, okay? Here, there is nothing written around, yeah, there is nothing written about in which direction the joint rotate. So we can either place X in this direction if we assume that the joint rotates counterclockwise, okay, or down if it is rotating. Sorry, we place Z up if we assume that the joint is rotating counterclockwise, and we place Z down if we assume that the joint is rotating clockwise, okay? So in this case, we assume that the joint is rotating counterclockwise, so we place Z up, and X has to be pointed along the perpendicular, okay? So this one is Z2, and this one is X2, okay? Now we can complete our little table. How do we pass from frame 1 to frame 2? Okay, is there any translation or rotation along the x-axis? Well, in this case there is, because I have to take the z that is coming toward us and put it from here to here, okay? So from perpendicular to the blackboard to upward, okay? And what does it mean? It means that I have to do a rotation along this axis, okay? So along z of minus 90 degree. How do I know that it's a minus 90 degree and not a plus 90 degree? Because it's always the same rule. I imagine to grab the axis with my hand, okay? And the fingertips tells me in which direction there is the plus, okay? So if I move along this side, okay, is rotating like this, then it is a positive direction, otherwise it is a negative direction. In this case, I have to move the frame from this to this, okay? Therefore, I have to do minus 90 degree. And there is also a translation of exactly 1. Therefore, we have 1 minus 90 degree. And then, is there any translation along the z-axis? Well, no. In this case, there is not. And then, there is also, in this case, a rotation along this new z-axis of theta 2, because this, this joint can actually rotate, right? So this one is theta 2. Now, we have to place frame 3, but we have to place frame 3 with respect to frame 4, that is already given, okay? So, let's try to be a little bit clever. How do we do this? Well, this one is the z-axis, okay, of frame 4. This one is the z-axis of frame 3 that is coming outside of the blackboard. What is the perpendicular between the two? Well, once again, is the line that connects the two, well, that goes along the link, okay? Therefore, the origin of frame 3 is placed here. So the intersection between the axis that is coming outside of the blackboard and the perpendicular. So here there is the origin, and now I have to place the Z3 along the axis of joint 3. Therefore, let me do a line like this, okay? Even though this arrow actually would be outside of the blackboard, okay? But just to make you understand, this one, I drew it like this. Now, I have to draw Z3, X3 along the perpendicular. So, this is it. X3 along the perpendicular between the two. Done. And now, finally, I can write the transition from frame 2 to frame 3, and then from frame 3 to frame 4. Once again, in this case, there is a rotation along the x-axis, because I have to move the z from here to here, okay? So I have to go back from what I've done before. And in this case, there is a rotation of plus 90 degrees, okay? And a movement, once again, of 1, okay? Now, also in this case, there is no movement along the z, so there is no displacement there. Here there is a 0, and here there is a theta 3. And finally, we have to pass from frame 3 to frame 4, and notice that frame 4 is not a joint, so it won't have a variable associated to the joint, and therefore, the rotation in this case is once again minus 90 degrees, because I have to bring back z upward. So from this position, I have to go back. So I have to do minus 90 degrees. A translation along x of 1. And then here there is 0, 0, because as I told you, there is no actual joint variable. Okay, it took me forever to do this, but let's go on with the second point. We have to compute the transition matrix from 0 to 4 to obtain the forward kinematics. And as I told you also before, the forward kinematics, how it is obtained from the transition matrix, well, you just extract the last column, and the first three components of that last column tells you the relation between the x, y, and z of the fourth frame. In this case, it is the end-effector, and the joint variable of in this case, joint 1, 2, and 3. So given theta 1, theta 2, and theta 3, I can obtain the x, y, and z position of the end-effector via the relationship that I extracted from the transition matrix 0, 4, okay? So let's go on. I will go quite fast here because it's always the same thing, so it's not really, it's nothing new actually. I just place basically one after the other, all the same relationship. It's just that in this case, instead of the previous case, I have something that is a little bit more complex sometimes. So let's do the first one that is very, very easy. The transition matrix from 0 to 1. Well, in this case, there is no rotation other than theta 1. Therefore, as we have seen before, we are going to have the basic rotational matrix here that I can denote also in this form. Okay, this means a rotational matrix along the z-axis of theta 1, okay? Here, there will be no movement. Here, 0, 0, 0. And this translates into, it will be the last time that I write it, C1, so cosine of theta 1 minus sine of theta 1, sine of theta 1, cosine of theta 1, 0, 0, 1, 0, 0, 0, 0, 0, 1, 0, 0, 0. Okay? So this rotational matrix, this notation, mean exactly this 3 by 3 matrix. Good? So at this point, we are going to use exactly this table as we have done before in order to compute all the other matrices. But as you can see already in the second one from frame 1 and frame 2, we have 2 rotation and 1 translation, unless what happened before. So it's a little bit more tricky. And that's why I put this formula over here, because you have to be extremely careful on how to do this multiplication. Because it's not the same to do first one thing and then the other, okay? You will obtain different solution, and in order to obtain the correct solution, okay, you have to use exactly this formula. So do the multiplication on the left-hand side, you have to put the operation on the x, and on the right part, so here the operation on the x, so alpha and a, and on the right, the one on the z, so d and theta, okay? This one also translates into this form, okay? So that formula can also be translated, is a kind of compact formula to write also this, minus 1, okay? Basically, you will obtain 2 big matrices that looks a lot something like this. You have the rotational matrix, okay, along x of alpha I minus 1, okay? That is the 3 by 3 upper left block of this matrix. Here there are 0, 0, 0. Here there is a 1. And here there is just a I minus 1, okay? So this one will be a of I minus 1. This one will be 0 and 0. Why? Because it is a translation of a I minus 1. So let's say, for example, a of 1, that is this one here, okay? It will translate into a vector of 1, 0, 0 because it's a movement along the x-axis. That's why it's placed here this way. And this formula here describes the multiplication of this Rx times dx, okay? So this formula here, this structure of the matrix, this transformation matrix, this transition matrix describes all the operation along the x, okay? You have to multiply this for the transition matrix of all the operation along the z. Therefore, you have as upper left block Rz of theta I. And here you have 0, 0, di, because this one is a translation along the z-axis, okay? And this is why here we have always 0, because in this particular arm, there is no translation along the z, okay? Therefore, this is what I use because it makes more sense for me to do this sort of structure. Obviously, as I've done here, you can just replace this with this 3 by 3 block in which here there is cosine of theta 1 minus sine of theta 1, or theta I, sorry, sine of theta I, cosine of theta I, 0, 0, 0, 1, 0, 0, 0. So this one is a 3 by 3 matrix, and this one in the same way, but it is the formula in which there is 1 on the upper left corner, and then there is the little block of sine of cosine, sine, minus sine, cosine on the bottom part. Okay, so this one is also a 3x3 matrix, and if you do the multiplication, you will obtain the big formula for this transition matrix that is in the book. I think it's formula around 3.6, I guess, and it is just the multiplication of these two. Okay, but given this, to obtain these transition matrices, the best thing is to first compute the transition matrix associated to all the x part, x movement, and then the one associated to the operation along the z. And then you do the multiplication between the two. Okay? Now that we have done this, basically it's just a substitution game. I will not do that. Therefore, using this formula, this structure, I will just do for t from 1 to 2, okay? The transition matrix from frame 1 to frame 2. How do you do that? Well, you just do exactly this. So, what is alpha 1? Okay, because we are, in this case, I is equal to 2, therefore I have to compute the rotational matrix along x of alpha 1. Alpha 1 is equal to minus 90 degrees. Okay. Therefore, I will obtain something like this. Rotation along x, so 1, 0, 0, 0, 0. And then here I have cosine of minus 90 degrees. Well, actually, let me write p half minus pi half. And here I have minus sine of pi half. Here I have sine of pi half. And here cosine of pi half. Okay? Here I have 0, 0, 0. Okay? Here I have a 1. And now here I have to put the translation of along the x-axis. So A1, that is equal to 1. So it is 1, 0, 0. Okay? And here what is the cosine of minus 90 degrees is equal to 0. Okay? Therefore this one is equal to 0. This one is equal to 1. Okay? And this one is equal to 0, and this one, sorry, here it is obviously minus 90 degrees, minus 90 degrees, minus 90 degrees. Therefore, this one is equal to minus 1, and this one is equal to 1. Okay? And therefore, you obtain this matrix over here that you multiply by the usual rotational matrix that is very much like this. I will write it one last time. You have cosine of theta 2, so cosine of theta 2 minus sine of theta 2, sine of theta 2, cosine of theta 2, 0, 0, 1, 0, 0. Here you have 0, 0, 0. 1, and here you have 0, 0, 0. You do this multiplication, and you obtain exactly the transition matrix from frame 1 to frame 2. Once you have this, to obtain the transition matrix from frame 0 to frame 2, the only thing that you have to do is multiply the two. So the transition matrix from frame 0 to frame 1 multiplied by the transition matrix from frame 1 to frame 2 gives you exactly the transition matrix from frame 0 to frame 2. Okay? You go on with this path for all of the joint, and you obtain the transition matrix from frame 0 to frame 4, okay? So it is just a mechanical computation that I will not do here. And this gives you exactly the exactly the transition matrix. And given the transition matrix, the last column here, okay, this last column gives you the forward kinematics, because as you can see, if I know theta 1, theta 2, and theta 3, and I plug it inside this relationship, so let's say that theta 1 is equal to 0, theta 2 is equal to 90, and theta 3 is equal to 90, okay? If I plug in 0, 90, 90 into the first, second, and third element of this, I will obtain the x, y, and z position of the end effector. Okay? Now, next question. That is actually to find out the basic Jacobian, both with the velocity propagation and the other one based on the derivative of the position vector. So the question D is exactly the same as the one that we have already done. So the question D of finding the basic Jacobian for this manipulator directly from the vector from 0 to 4, well, you just take this vector over here, okay? So the first free element of the last column of the transition matrix from frame 0 to frame 4, and to find out the basic Jacobian, you just derive this vector with respect to theta 1, and you obtain the first column of the Jacobian associated to the linear velocity. Then you derive with respect to theta 2, and you obtain the second column of the Jacobian associated to the linear velocity. And then with respect to theta 3, you obtain the third column of the Jacobian associated to the linear velocity. To obtain instead the part of the Jacobian associated to the angular velocity, you have to look at the axis. In this case, they are all revolute joints, so you have to look at all the axes. And what you are going to do is take the last column of the rotational part of the transition matrix from 0 to 1, from 0 to 2, and from 0 to 3. In this case, for example, it is 0, 0, 1. So we already know that J omega has as first column 0, 0, 1. Okay, and here there is Z2 in frame 0 and Z3 all still in frame 0. Okay, and this is how do you compute the Jacobian associated to the angular one. Now there is the more complex part. Well, kind of. That is to compute the Jacobian using the velocity propagation. As you will see, is a tedious procedure. Also in this case, basically we already have everything we need. We don't need much, actually. And it's just a quite long procedure in which we have to compute the velocity of frame 1 expressed in frame 1, frame 2 expressed in frame 2, and so on and so forth, in order to achieve exactly the relationship that expresses the velocity of frame 4 expressed in frame 0. Okay, as you will see. And since we have only the rotational, joints, we are going to use only the first formulas that you see over here. Okay. And I will do the first two joint, and then you can go on by yourself, because as I told you, it's pretty easy, but just very long. And as a tip, if you can, I would just suggest you to use the other method to compute the Jacobian, so just to derive the vector from 0 to the end-effector. Okay, because it's much faster. The problem is that sometimes you don't have that vector. If you don't have that vector, or if it is explicitly asked to use the velocity propagation, then use it. Historically, it's very useful because in this way, you can compute the velocity of each point of your kinematic chain, and not only the one at the end-effector. And it's also the easiest way to do that for a calculator, because they are just multiplication and that's it. Very easy for a calculator to do that, but for a human it's quite tedious. So, keeping a look on this relation over here, okay, so the first two for the revolute joint, let's try to write down the omega 1 expressed in frame 1. So, omega 1 expressed in frame 1 is equal just to 0, 0, theta 1 dot. Why? Because there is no previous joint, so this omega here is 0, 0, and there is no kind of rotation, so there is no angular velocity here of the 0 frame. Therefore, this first part of the relation is equal to 0, and you only have the second part. Obviously, the axis here is 0, 0, 1, so you have to multiply theta 1 dot times 0, 0, 1. Therefore, you obtain as angular velocity of frame 1 measured in frame 1, 0, 0, theta 1 dot. Okay? And now, what is the linear velocity of frame 1? Well, if you think of how the robotic arm is constructed, there is no linear velocity because the 0 frame is placed exactly on top of the 1 frame, so there is no linear velocity of the 1 frame with respect to the 0 frame. Therefore, it's just a vector of zeros. Okay, now let's go for the second frame, and we have that omega 2 is equal to, now we have to multiply the rotational matrix, okay, 2 to 1, okay, times this vector over here, so 0, 0, theta 1 dot. And then you have to add the other part, that is just the rotation, okay, along its own axis. Its own axis, as you can see here, is z I plus 1, so the axis of the frame I plus 1, in this case the second frame, but is measured in the second frame. Therefore, it will always be the vector 0, 0, 1. Therefore, this part will always be 0, 0, theta 2 dot. Okay? Now, where do we get this rotational matrix over here? Well, it's very similar to what we have over here, right? Because this transition matrix is done in this form, right? This one is the rotational matrix from 1 to 2. 0, 0, 0. This one is 1, and here is basically the position from 1 to 2. Okay? And but this rotational matrix is not what we need. We need the rotational matrix from 2 to 1. Instead, we have from 1 to 2. But it turns out that it's very easy because the rotational matrix from 2 to 1 is just equal to the transpose of the rotational matrix from 1 to 2. So to obtain these matrices over here, the only thing that you have to do is extract this 3 by 3 matrix and do the transpose, and you are done. Okay? So you do the transpose, you obtain this matrix, you do this computation, and you obtain this. Minus sine of theta 2, theta 1 dot. Then you have minus cosine of theta 2, theta 1 dot, and then theta 2 dot. Okay? Fine. And now a little bit more tricky part. Okay? So in this case, we have that V2 is equal to, once again, R21, so the same matrix as before, and then we have all zeros, so we don't even write it, and then we have to do the cross product between 0, 0, theta 1 dot, cross product with the vector that connects the axis, the frame I to I plus 1. In this case is 1, 0, 0. Okay? And okay, so okay, and this gives you exactly this 0, 0, theta 1 dot. That, if you think about it, makes sense, because this one is just a rotation. Okay, if we go back to the schematic of the arm, it is this one, okay? It's just a rotation of theta 1 dot, so as fast as theta 1 dot, and of length 1. So you go on with the same structure, you do all this computation, and you arrive at the solution that is, and you arrive to V44 and the angular velocity 44, okay? But these two are the linear and the angular velocity expressed in the frame 4. What you need to compute the basic Jacobian is these two, but expressed in frame 0. How do you do that? Well, it's easy, because you just have this nice relation that tells you that if you pre-multiply this by R, you obtain exactly what you want. So V from 0 to 4 is equal to R 0, 4, V 4, 4. And the same thing here. Okay? And this gives you the true velocity expressed in the 0 frame. At this point, the exercise is completed. These are the two formulas, because is exactly the only thing that you have to do is extract the Jacobian. That is fairly easy. You just have to see what theta 1 dot multiply, theta 2 dot multiply, and so on. Now, since we went a little bit long on this part, I will give it to you as an exercise to compute the singularity of the arm. You will see in the solution that is very easy, because the only thing that you have to do is, first they ask you to compute the Jacobian in the one frame. How do you do that? Well, also in this case, we are lucky, because because also in this case we have a relation to relate the Jacobian. In this case, they are talking about the Jacobian related to the linear velocity, okay? How do we compute this relation? So something that relates the Jacobian, the basic Jacobian associated to the linear velocity, to the Jacobian associated to the linear velocity by expressing the frame one. Well, you just multiply by R1, 0. Okay? And you obtain exactly this Jacobian. From this, okay, from this quantity, why they ask you to do that? Well, just because in this form the Jacobian is much easier, and you just have to compute the determinant of that. When you have computed the determinant of that, you just put it equal to 0, and you obtain the singularities. You will see in the solution that they are very easy, and it's also easy to understand what they mean from a physical point of view. From this, I concluded the second tutorial. Okay? And yeah, so this one is the Jacobian, and these are the physical interpretation, but you will see everything in the solutions. With this, I completed the second tutorial. I hope this was helpful. If you have any question, I know that it's maybe difficult to follow only from video, and maybe I don't know if you can see exactly all the computation, but if you have any question, please let me know, and I will try to reply to you as soon as possible. And thank you for your attention, and good luck with the exercises.